Okay, sir.
Okay. So once again, I welcome you all here in the second day of our FDP. So today's session, first session, which will be from 6 p.m. to 7:30 p.m. On advanced supervised learning by Dr. Pravin Ramteke. Presently, he is working in SIDAC, Mumbai. He is working as a knowledge associate in Language Lab, Government of India, SIDAC. He is having around 15 years of experience. He did his PhD from NITK Surathkal, Computer Science and Engineering Department. He has around 30 research articles, including in journals and conferences, conference proceedings. And his expertise is AI/ML, artificial intelligence and machine learning. And actually, he's working in language lab only in SIDAC. I think he's having enough expertise to explain what exactly or what are the advanced supervised learning algorithms. So I request Pravin Ramteke sir. I first welcome him, and I request Pravin Ramteke sir to take over the session.
Thank you, Raman sir. I think I want to share my screen, so can you please?
Yes, Manoj sir, you.
Hello, sir. Now you can present, sir.
I hope my tab is visible. I will go for slideshow. Slideshow is visible?
Yes.
Yes.
Yes. So thank you all for joining for this presentation in FDP AI revolution from machine learning to generative AI. So my topic is advanced supervised learning, introduction to LLMs. Mostly the first part of the LLM, we know that pre-training is unsupervised. But still, I decided to take it as a part for my presentation. Let's go introduction to the LLMs. So basically, what is a large language model? As everyone is using ChatGPT every day, I think, for generating codes, for writing applications, for asking anything, whatever they want. Even some people are using it for chatting also with ChatGPT itself. So it's basically a deep neural network, specially designed to understand and generate and respond like human text. As we know, when we type or we ask anything to ChatGPT, it responds like the way we talk. So basically, the neural network, as we all know, it is input layer and some hidden layers in between and the output layers. So what it means to understand, generate, and respond like human text. As I explained, whenever we ask question, what could be the best plan to roam around the Konkan region? If I type it into ChatGPT, it will give me the entire plan, or it will plan a basic trip for me. So which places I can visit, which places I can go around for scuba diving, what are the temples I should visit there, is the famous places there. So that way. Then why it is called as large language model? Basically, the large keyword. Why large? It is because it has been trained on the billions of parameters. It's a large network and it has been trained on billions of parameters. So from there, the large word has come. So we can see these models do a wide range of NLP tasks like question answer, sentiment analysis, and language translation, anything. The basic or secret sauce in this LLMs is transformers, which we are going to see in the upcoming slides, where it has been, I think, introduced in the paper that attention is all you need, which has been published by the 8 authors from Google Brain. If you go on the Google Scholar and search this paper, you will find, I think, around 100,000 citations to this paper. So move to next slide. So here I would like to tell you that from here this large word has come, introduction to LLM. So here you can see GPT small is available, number of parameters are 125 million parameters are there. Where you come to GPT-3 175B, which is the largest model, 175 billion parameters are there. So basic difference between LLMs, Gen AI, deep learning, machine learning, and artificial intelligence. So we can consider it as a subset and superset game where AI is the broadest part of it, where you can think of any rule-based machine which just responds to your ask queries or the task which you ask it to do it. So like the basic rule-based chatbots, which does not have much intelligence in them, that also comes under the artificial intelligence, which we can say that anything which which tries to behave like a human has some kind of intelligence, which comes under artificial intelligence. Then the subset of AI is ML. So ML is basically the neural networks plus the other fields, like the other models that we have, supervised learning models support vector machines or decision tree comes under machine learning. Then comes the deep learning part, which is the subset of ML, where we can think of only the neural networks, where we can say mostly we perform the task of image detection using CNN and digit detection, or any kind of regression or classification task performed using deep learning or neural networks. Then comes the LLMs. LLMs is a subset of deep learning. Mostly deals with the text, or I can say that only deals with the text. Then we go for the generative AI. I think in coming subsequent sessions, you will be having introduction to generative AIs and I think LLMs in depth also. So generative AI is a mixture of LLM plus deep learning model. It can be used for various tasks like generate a new text content or various forms of data media. So I hope the difference between AI, ML, deep learning, LLMs is clear to you. So we can say we will see now the stages of building LLMs here. So it can be broadly divided into the pre-training and fine-tuning part, where the pre-training is just training the LLMs or LLMs on the diverse data set or diverse text of a document, which is we can say which is not labeled. And this pre-training leads to the foundational model, which can be used for various tasks. Here, actually, the interesting thing to tell you is the LLMs have been initially built to just recognize the subsequent word. Like here, example I have mentioned here, I need money for, and then I left a space blank, which I want my LLM to predict. So this was the basic task of the LLM. Then there are some questions about this, that how efficiently the LLM can interact, how efficiently it can answer the user queries, how it is able to understand and speak like a human or write like a human, and how its answers are so accurate. So the entire logic lies behind the training data, the huge training data and diverse data it is trained on. So initially, when I can say the people who were working on the LLMs, they might not have thought that these LLMs is going to be this revolutionary, because their aim was to just predict next word. But when they tested it on the different thing, so without training on those specific tasks, it has given very good output. Some Vendata application is there, they are using it for MCQ generations, translations, summarizations, and so many different tasks. So I think the second stage is the fine tuning. So now when you get the foundational model, which is the pre-training, it is a generalized model. You can ask or perform any task on it. But let's say if any company or any organization wants to fine tune that foundational model for their need, then comes the fine tuning or refinement of that model. And here actually we use the labeled data. In the previous pre-training, we were not using labeled data. There actually which means I'm not saying that exactly not labeled data, but here there in pre-training, the previous words are input to the sentence, and the next predicted word is the output for that. And when we go for the next iteration, the current predicted output will be considered as the input to the next iteration. So that way it trains itself. But let's say I want to build a specific chatbot for an airline company. So in that case, we need to give a labeled data so that my pre-trained LLM or foundational LLM could, I can say, reply in a fine-tuned way to that particular query. Here I have mentioned an example of Harvey AI legal tool for attorney, which was trained on legal cases history. So it has been observed that when they tried to use this tool, 83% in the factual responses have been observed, and people preferred to use means 95% use 97% from the analysis. It is observed that 97% people were using this fine-tuned AI model rather than the general chat GPT. So fine-tuning is basically needed when you go for a specific application. So these are some stages you will find. Sorry for my bad slides. These are the handwritten notes which I have screenshot and pasted here. So basically for LLMs, we can see here that input is input text, books, research, from wherever we get the text data, that is raw and unlabeled text data. Trillions of words are there. Then we train the LLM, which results into pre-trained or foundational model of LLM, and then based on the labeled data, we just train this pre-trained or foundational model. A pre-train is just a trained LLM. It is just a terminology thing, LLM, and we can fine-tune it for different thing like classification, summarization, translation, personal assistance, anything. So we'll move to next slide. So these are the basic steps while building the LLM. So train on a large corpus of a text. You can see raw text, which is a regular text without any labeling. So first training stage of LLM is also called as pre-training, which I have already explained. So it is creating an initial pre-trained LLM, which is a base foundation model, which has been used by this ChatGPT 3 for text completion tasks, which I said like LLMs have been traditionally trained to perform these tasks, that is a text completion task. Then fine tuning is the next part. As I said, it can be deployed to make LLMs to perform on the specific task. As some examples, text translation, airline, customer support, text translation company, you can see, give instructions or a sentence in French and English. So basically the language translation. Even classification tasks can be like, as we know, emails classification, spam and non-spam emails. So the most modern LLM rely on the transformer architecture. As I said, there is a source, we can say, there is a transformer. So the transformer is basically the deep neural network itself. It has been introduced in the paper 2017, that attention is all you need, which as I mentioned previously. So the foundational stone or block of the ChatGPT originates from this paper. Then next is it's just the information which I have mentioned. Transformer architecture is not exactly same, which is mentioned in this 2017 paper. Which actually, whatever we use for training LLMs, it has a only decoder model. While the paper in the 2017 published attention you all you need is having encoder and decoder model, but that's not the major point of discussion here. Just I wanted to mention the difference between the attention you all you need paper architecture and the LLM paper. So basically it makes very important to study this paper to get the thorough insight into this LLMs or the transformer architecture. So basically what it basically I want to mention is the transformer works on the attention model. As everyone have might have studied or heard about attention model, it was in trending. So it is like just how much importance should be given if I'm processing a sentence or let's say I'm performing a task of text completion. So how much importance should be given to the previous words while predicting the present word. So that actually the attention means. We will see in the details in the later slides. So this is basically the snapshot or screenshot from this paper 2017, which shows the transformer model architecture. So here you can see some terminologies, that multi-head attention, multitask attention, uh, then positional encoding, input encoding. So that also we are going to see in the upcoming slide. Just look into this model. So we will go through this transformer architecture in a simplified way, which I tried to study and what I could understand from this. So the simplified transformer architecture is like, let's say, as I said, this is a language translation task. In 2017 paper was specifically built for this language translation task. So this has been interpretation has been taken from that paper. So this is an example. It has to be translated to French. Das Estin Bespel. So the input text will be this is the input text will be taken, and it will be pre-processed, and it will be converted into let's say vector embeddings. Okay, so with the help of encoder. So there are stage pre-processing. It will convert the entire sentence into the tokens, and then it will be fed to encoder. It will encode the just it will be convert the words into the vocabulary format. Like you will have the unique ID on one side and the labels on the, or the words on the one side, and then these labels or the IDs will be converted. These encodings will be converted into the embeddings that we are going to see in the upcoming slides. And similarly, the partial input will come from the French language. Here you can see this will be similarly, it will be pre-processed, like tokenized and encoded, and that will be given, both the inputs will be fed to, like the output from the embedding, and the pre-processing step will be given to the decoder. So based on the embeddings here and the encoded information from this partial output text, its decoder's job is to decode or generate the translation one word at a time. So let's say in first iteration, like if I just give DS as an input, in the first iteration it will predict this ST. Then in the next iteration it will produce the Baspel. So that way. So basically, it is like predicting the labels or the output one at each iteration based on the received embeddings and the partial information. So this is how the transformer works in the 2017 paper. So here also you can see the generalized or unfolded way of iteration. Sorry for this markings here. I have taken this a snapshot from someone tutorial. So here also we can see this is another way, like as I said, the another task. So that sentence completion or the next word generation task. So here I have fed this as a word as a input to a transformer. Then it has performed the pre-processing, like tokenization, encoding, then embedding, and then it has been fed to decoder. Now remember the point I have mentioned, the LLMs only have the decoder phase and not the encoder phase. So it has been given to the decoder, and then the output layer predicts the next word. So this is predicted. Now, as I said, it has an auto. I'm mentioning the one term here, auto regressive. So how come it how it is an auto regressive? Because the output of this one, this first iteration will be considered as the input to the second iteration. So this is the input to the second iteration of the same transformer model. Again, it will go through the same procedure and it will decode the next word from that. This is then an. Then this output is considered as an input to the third iteration. So this is an, and the final output will be the example. So this way the transformer works. So now we are going to see these steps one by one. If time permits, I will go beyond the let's say attention's basics. So introduction to this transformer. What is the pre-processing? We have mentioned pre-processing step there. So here pre-processing consists of the tokenization. So why tokenization is important? Because we cannot feed the entire sentence directly, and even if we feed the entire sentence directly, it will be very difficult for us to encode that whole sentence and feed it to the neural network and get the output. So what we do is we divide the sentence into a single tokens. For now, we will consider a single word as a token. Later, we will come to the stage where I will explain what token is, how it has been generated using BBE algorithm. So the one word is exactly one token. Here I'm mentioning, and it assigns a unique number to each token. Okay, that the way we do it in a vocabulary. So we know that the transformer earlier has a two part, that is encoder and a decoder. So encoder, the task of the encoder converts input into the embedding vectors, which is very important. These embedding vectors are considered by LLMs or GPT models for this training their model. Then the decoder generates the output text from the encoded vector plus the partial input received from the previous iteration. Okay, so here it's vector encoding. So this is the basic sequence of generating the vector. Like we have a sentence, then we divide it into the words, which we are calling now as tokens, and then assign ID to it, and encode the semantic meaning between the words. Now, if I embedding, why we go for the embedding, not just encoding, because encoding just assigns a unique ID to a particular word, but it does not capture or fails to capture the semantic information between the words. Let's say boy and boys. So it will simply, if we do not properly tokenize it, it will simply assign a unique ID to boy and boys. It will not say that it will be those two words are similar. So it loses the semantic information. And somewhere like cat and kitten, they are also I can say very close words, but encoder simply fails to encode that relation information, where as the vector embedding tries to capture that information. So the key part of the transformer architecture is self-attention mechanism. That also we are going to see. So this is attention. What it does is, as I explained earlier, allows you to model dependencies between two words without considering how close they appear in the sentence, or how far they appear in the sentence. And the self-attention is a mechanism relating to different position of a single sequence in order to compute a sequence. It is basically we can say that it allows you to measure the importance of a different word relative to each other. That is the only thing. So here I have a two sentence like Harry Potter is on the platform 2 and Harry Potter boards on the train. So when you are trying to predict the last part or the last next word for this or the new sentence for this conversation, it may happen that the platform information is required while generating the next sentence or the next word. So the attention model, what it does is it keeps a track of these words, or it give based on a particular key. It tries to assign the attention to particular words and use those words or consider those words while generating or predicting the next sentence or the word. So as I mentioned, like it enables to capture the long range dependencies. As I said, like the platform word may be needed while generating the third sentence or the fourth sentence. So it maintains attention score for each token word. Like if there are some, let's say platform word is there. Now I want to know that how close this platform word is to the porter or to the number. So this has been calculated based on the attention score, that we will see how it is being calculated. There are certain versions of this, two versions of this transformer model, which you might have heard, that is BERT model, and then the model we are using in the GPT. So BERT is nothing but bidirectional encoder representation for from transformer. So it predicts, basically it predicts, it can traverse the sentence in both ways. as it is bidirectional. So it is very efficient in predicting the missing words or the hidden words in the sentence. As you can see here, this is an here's a blank space which it has to predict. Basically, it is better to for these type of tasks, or we can say that it can also be used for sentiment analysis, because it can travel back also. So it can travel back and forth, so it can get a given a paragraph, it can get a complete essence of this paragraph and label it as whether it is a positive what sentiment it has. Okay, so it is able to differentiate, means the power of BERT is that it is able to differentiate bank as a river and as a financial institute based on the context it has appeared in the sentence. Then we are going to see the GPT. GPT learns to generate one word at a time. In the beginning, I have said this was the basic task of this. This is an example of how LLM can. So it's out. Its basic aim is to predict this next word. Now the transformer versus LLMs. So we can say that not all transformers are LLMs, because transformers can be used for different tasks, from image recognition, classification. We can say the task which CNNs are able to perform. That way, the transformer can be used to do this. While the LLMs are basically for language-related models only, or language-related tasks only. And it is important to note that not all LLMs are transformers also. So LLMs can be considered, the earlier RNNs and LSTM model, the language model built on this, can also be considered as an LLM. So LLMs, as we all know, that it is basically maintains one final states for all the iteration it has to go through, and it passes that final state to the decoder so that it can decode the sequence. If I consider a language translation model, then it will have an hidden state which will have all the information related to the translation, and that will be passed to the decoder, and the decoder, based on that hidden state, it will generate the sequence of the given input. Similarly, the LSTMs are also there. These are the famous models which we all know, so I'm not going into the details of this. So having a closer look at LLMs, basically the real boss is, we can say that short learnings. So language models are few short learners. This is the 2020 paper and GPT-3. So which can be used for different types of tasks. Means GPT we will use for different types of tasks using this. So translation, sentiment analysis, emotion detection, etc. So first comes is zero shot. It is like nothing but we can think of GPT in a generalized way. We just type something without giving a context of that. Just we type the problem and it will give us the solution. So it is an ability to generalize the unseen task without prior specific example. So here you can see the example I have mentioned: translate English to French. So this is the task description, and I have simply given the word or the prompt. So it will just translate it to the French. So this is zero shot. I have not given any prior information. Then comes the one shot. So in one shot, in addition to the task description model, it sees a single example of it. Okay. So here you can see the example: translate English to French. So this is the task description. Then I am providing one example to the LLM, that is the Sea Otter. So it's a French translation of that. And then I'm typing cheese, and I'm expecting LLM to give output, or GPT to give output of French translation of cheese. So this comes under one shot. Then comes the few shot learning. So it is nothing but learning from a minimum number of examples the user provided as an input. It depends on the context, like how many minimum examples you want to give. Here 3 examples have been given, and the prompt has been expected as a cheese here. So mostly people are attempting this zero shot way to get the output, so that they need not have to give examples and all. So this is the crux here. We'll move to next slide. So it comes stages to build an LLM. Sorry for the spelling mistake. It should be an. So there is a building stage for the LLM. So we have first step, as I mentioned, the data preparation and sampling. So which comes in which includes the tokenization, then divide the data into batches, then prediction task. Like it is just like how many words should be taken for training at a time for each iteration. We will be having like the data, as I said, the one input sequence I'm feeding it to, so it should be of length 4 or length 5 or length 6. So in the previous example, if I could be able to share my screen, I think I have shared my tab here. I was unable to share my screen, else I would have shown that screenshot. So here it will come in the subsequent slide. There I will explain. Then the positional encoding. Positional encoding is just first, before that it is vector embedding. So it captures the semantic information between the words. So given the sent list of sentences, it will be tokenized. Okay. Then it will be uh, converted into the vector embedding representation. Along with this vector embedding representation, positional encoding will be added to it. Positional embedding or encoding will be added to it, and so basically the vector embedding captures the semantic meaning between the two words, where they lie in the sentence. It doesn't matter. Then the positional encoding is given a sentence at which position that particular word comes. Let's say cat sat on the mat and mat sat on the mat, cat sat. So these are the two words where the position of the subject, like the cat, is different in both the way. So this may lead to this is the contextual information which we have. So which actually vector embedding is failing to catch, but the positional encoding or embedding, it captures, because we add an extra embedding or encoding to the embedding to the vector embedding, such that it will have that positional information with that. So wherever, let's say if the cat is coming in the beginning or at the end of the word, so the LLMs can take decision for that type of situations. So attention models, mostly the multi-head attention and masked multi-head attentions are used, as you can see in as we have seen in this architecture, which was published in 2017 paper. Um, so we are not going to go into the details of multi-head attention or mass attention. I think the upcoming sessions will cover these in details. My aim is to just go through this attention model into the details, and the data preparation part into the detail, because these are the most complex things to understand how it is been done in the I can say LLMs. So you can see pre-training, how the pre-training is done, or the how the foundational model is being generated. So you can see here, building an LLM, it requires data preparation and sampling. Again, sorry for this handwritten diagram. So which has building an LLM, which takes data preparation and sampling, which is the first step. Then the attention mechanism, we need to design the attention mechanism, and then the LLM architecture. So based on these inputs, our LLMs will be pre-trained, and we will get the foundational model. Here, I think training will be done, then model evaluation will be done, and loop pre-trained weights has been will be done to achieve the I think stable model here, and then this model will be fine-tuned so that we can use it for a different application. So here you can see we have break data into an epoch. As I said, we will be tokenizing the words. Then how many words should be considered for this training purpose, like four words at a time or 5 words at a time. Then the fifth word will be predicted by the LLM. So that way, then compute the gradient of each epoch. So this flow diagram basically shows how the training is being done. This I have just mentioned into the 4 points. Then update the parameters and generate the sample text for the visual inspection. So this is how we usually train the neural network. These are the basic steps, like go through the training loop, computer gradient, update the parameters, and then generate a sample text. If there is a evaluate the error, and then again retrain the model. So you can see here for each training epoch, for each batch in training, then reset the loss gradient from the previous epoch, and then calculate the loss on the current batch, then backward pass to the to calculate the loss gradient, then update the model weights using the loss gradient, print training validation. So these are the basic steps which I have mentioned in short in 4 points here. The next stage is model evaluation and load pre-train weight. So in order to fine tune the model, as we know, the training cost is very huge while building the LLMs. So what we do is, whenever we finish some cycles of training, we do not scratch the next we do not train from scratch again. We will save the weights and load it again, and then we will train the data on that. So here you can see the text generation, then text evaluation, and then training and validation loss. Then we perform the LLM training here. Then we decide the text generation strategies. So it implements additional. Here we are not discussing this part for additional text generation strategies to reduce the data training memorization. But whatever the output of this will be saved, and whenever we go for fine tuning the model, not fine tuning exactly, we will go for updating these pre-trained weights. So we will load the existing saved weight, and sometimes we will be using pre-trained weights of the OpenAI. So those are available freely. Anyone can use them for their specific task or build their own type of LLMs. So last stage is fine tuning. That it will, if I explain it again and again, it will be the repetition every time. So still I will see that this is the spam and non-spam email detection has been performed using fine tuning task. Then so basically the transformer architecture. So key mechanism here, or key idea, that the LLM gives selective access to whole input sequence when generating the output one word at a time. So this we will come. So this thing allows LLM to understand the importance of words in the current sentence to generate the next word. And this also helps it or keeps in a memory the some words which have been appeared long back into the we can say into the that particular context. Basically, which I mentioned earlier, I had mentioned one thing that LLMs have been just means the task was to just detect or generate one word at a time, output one word at a time, or complete the sentence. So we, after testing, the people who have tested for different tasks, they have found a tremendous capacity of this LLMs to perform the wide range of tasks. So that the properties which actually the LLMs has not been trained for has been given a special term, that those are called as the emergent properties. Okay, so remember this term, the emergent properties means the model which has not been trained to perform those tasks, but it is able to perform those tasks. So that comes under the emergent properties of that particular model. So now we have come to the tokenization thing. So working with the text. So what we do is the process of breaking down the sentences into individual tokens. So as I explained earlier, it comes under the data preparation and sampling. So how do you prepare input text for training an LLM? So first thing is splitting text into individual words and subword token. Then convert the tokens into the token IDs and encode those token IDs into a vector representation that is called as the vector embedding. So this is basically the simple example. Again, this is handwritten thing. So this is an example which is the input text. I have tokenized it. That is this vertical bar represent just I have separated the token. Then I have assigned this. I have sorted, and let's say I have a text pool, and I have sorted them and assigned the ID to that, and that is called as a token ID for this. And then this has been converted to vector embedding that we are going to see in the next thing. So this is actually along with this vector embedding, along with the positional embedding or positional encoding, is being fed to I can say GPT or GPT model for training. So this is how the tokenization has been done. This is the basic Python program. I will share my screen and I will show you how. So the data set used for here in this example is the verdict book written by the Edith Wharton. So you can download. This is freely available and is being used by many people for demonstration purpose or simple building a simple these models. So basically in Python we are going to read this file. So I'm not going to show this on the terminal because this is a simple command with open. We can just read this file and display the raw text. So basically this is the output. The total number of characters in this document is 20,479, and some sentences I have displayed, first 100 sentences. So these are the sentences. Now goal is to tokenize. Our goal for this is, the goal is to tokenize the words in this book and the special characters that which we can use as a vector embedding for training LLMs. So this is working with, we are using the RE library for regular expression to split the given text into white spaces. So here just it simply divides the text into based on the white spaces, but it do not separate these it based on the like commas and these special characters, punctuation marks and all. So it can be updated, this statement that re dot split can be updated as given here. The re dot split, we can add any number of punctuations or special character based on which we want to separate out from this. So this is what I was talking about. Main task is like white spaces appears in every text, and if we want to consider a white space, it is going to take a huge amount of memory and huge amount of computation is required for that. So but keeping them, it completely depends on the application, which application you want to build, whether the spaces you want to keep or you want to exclude them. Basically, it has been mentioned that whenever you are using it for code generation or type of task where, especially for the Python code, where indentation and spacing are more important, it is advised to keep the spaces here. Otherwise, for remaining tasks, it can be excluded because whenever the decoder generates the we can say the token ID, and then from token ID we generate the word, the spaces will be added in between. This is the procedure how to convert the tokens into token ID. This is the numerical representation. So I have this sentence: the quick brown fox jumps over the lazy dog. So based on the above program, just I will be tokenizing it by separating it into white spaces, by white spaces. So the quick will be one word, then token, then the is another token, brown is another token, and fox is another token. So from this we are going to build a vocabulary, which is actually the token and ID. As I said, the encoding part, it has come here. So whichever the words, let's say I have scanned thousands of documents and I have generated the tokens there, and I will then sort them in the alphabetical order, and from the first word itself I will keep assigning a unique ID to that. So you can see here 0, 1, 2, 3. Let's say I have only these words in my vocabulary, so I have started from B, F, Q and T. So 0, 1, 2, 3 is the token ID for them. So basically it is like assigning a unique integer or unique ID to each token. So as I mentioned, that vocabulary, it is just the token ID in encoding. So I have a Python code where you have an encoder function which actually converts this sentence or a given text into the token ID and encodings. And while decoding, actually, when you say that the decoder decodes the text, So that way it does not directly decode the text. It will give you the embedding, and from the embedding we will be getting the IDs. So those IDs need to be mapped with this vocabulary. So we need to prepare the reverse version of that also. So where the token and respective ID is also there. So now we have token and ID. So the representation for ID and token need to be prepared. I will try to share my screen and I will show you that code. Wait for a while. Just sorry, I'm unable to share my entire screen, but this is the code which I have written here. So here you can see this is the text which I want to convert into the tokens. This is the text. That text, hello world. This is the text. Then result I have splitted, and you can see here it has been vocabulary has been created in the res. So here basically what I'm doing is I am just assigning ID to each token. So here you can see, sorry, here I am assigning, here only I am getting the tokens, unique tokens. Then this statement you can see here I am preparing, creating a vocabulary where I am assigning token and integer. So this is my vocabulary which has a token and respective token ID for that. Then the reverse of that is we can say here the flip the token and the token IDs. So this is going to give me I can say the reverse version of my vocabulary which has ID to word mapping. I would have executed that code, but it's not allowing me to share my entire screen. So I'm extremely sorry for that. Okay. So
Yes, sir, your screen is visible.
no, screen is visible, but I am unable to edit. So unable to go to that. Sorry.
Okay, okay.
Yeah. So I don't know from where this. So it's okay. I think I will. Yeah. So I think I'm visible now.
Yes, sir.
So now the tokenizing with a special context token. So what happens is, let's say I have downloaded that particular book, and let's say I have some words which I am giving as an input for tokenizing, but at present my the words I'm giving input to my vocabulary to encode or to get the ID from that token ID and token, it does not have that word. So what should be done in that case? Or let's say I am parsing multiple documents, but how my program will know, or how the LLM will know that while my tokenizer will know that I have reached the end of the text or end of the document. So there are two you can say modifiers are available, that is the unknown modifier, or it is a context token, and the end of text context token. So these have been used. The unknown is mostly used whenever it will add that particular word to this tag. Whenever that particular word is not in this, I can say vocabulary, and end of the text is always added at the beginning of the document to represent that they are starting the new document, or at the end of the document to represent that it has been like that you have reached to the end of the document. I have examples for this also, to how to add this encoded text, these two context tokens to this vocabulary, and then generate the tokens. But as I'm unable to share the screen, it is difficult for me to show you the demo. So now let's say after adding this unknown context token and end of text token, always you will get the higher number here, as it has these two tokens will be always appended at the end of your vocabulary. Okay, so these should have been actually in a sequence, but by mistake I typed different numbers here. So let's say it's 9875, then 9874, then end of text token will be 9875. So here I have mentioned a specific word, that quick word is there, but exact matching, as we are treating each word as a token, quickly is not present in my vocabulary. So what it will do is it will assign a token ID of unknown to it. You can see. There are some other tokens also. The BOS, the beginning of sentence, it marks the start of the text, signifies LLM where a context or a sentence begins. Then end of sentences, which is position at the end of the sentences. It is basically used to concatenate the text which are, I can say, in different in nature. Let's say Wikipedia page and book, or let's say newspaper article. So that way. And the padding is also an important token. Because somewhere when we divide our input vectors into the batches, let's say there may be an input mismatch in that case at the end of the we can say end of the embedded vector or encoding embedded vector. So in that case we will add those many elements into this we can say embedding, so that the input size is matched to that. So generally the LLMs which are using the GPTs, they only need end of text tokens, and does not need any other token, because by byte pair encoding we are going to see this algorithm also, BP, that breaks words into subunits, such that mostly if you have a very large corpus with you, it will automatically deal with these unknown tokens, or the tokens which are not present in the vocabulary. So we have come to the byte pair encoding. So it is mostly used in LLMs and GPT to generate the tokens. So there are basically three types of tokens. One is word-based token, then sub-word-based tokens, and character-based tokens are there. So we will see first the word-based token, as previously we were considering that every word is a token. So problem is that you may run out of vocabulary. As I have mentioned, there may be some words, if your vocabulary size is limited, then in that case you may run out of vocabulary. Then it is difficult for you to capture the what can say the meaning of the similar words, or the meaning of a word in a different context. So we'll not discuss context here. Similarity is not captured, like boy and boys will be treated as a different. Then the character base. So here individual character is considered as a token. We can say that it solves the vocabulary problem, but it leads to the another problem, that if I divide a sentence, if I have a huge amount of document and if I divide it into the character based tokens, then I will have a large tokens, and it will be very difficult for me to process those many tokens. Means lots of resources will be required, and meaning associated with the words will be lost here. That is the more important drawback of this character based tokenization. So the middle way comes here is the subword based token. So here there are two rules basically we follow, that do not split the frequently used words into smaller words, and split the we can say rare words, sorry for the spelling mistake here, rare words into the smaller meaningful subwords. So we can say here the boy, if in my in my documents, lots of documents I have, if boy is frequently appearing, do not split it. But related to that, if boy is coming, then split that word into boy and yes. So this helps the model to learn the different type of words which has the same roots, like tokens and tokenizing. If I remove izing from here and s from here, it has the same root, and also helps to help the model to learn the words which have the similar ending. Means they have the different roots also, but have the same suffix. So we will see one of that we can say this subword based algorithm. It is a byte pair encoding. This is an algorithm which have been proposed for the data compression in 1994. Even that time, I think authors were also not aware of this, that this algorithm will be used in such a task also. So most here the algorithm works in such a way that the most common pair of consecutive bytes of a data is replaced with a byte that does not occur in a data. So let's say I have, for example, I have original data is AAA B D AA BAC. So the byte pair is A, as I said, byte pair. Okay, so AA is a pair, occurs the most frequently. As you can see, it appears at two places. So replace it with the character which is not appearing in it. So we will replace it with Z. So the string has become ZAB DAZA BAC. So similarly, we can find the next byte pair is AB. So we replace it correspondingly. So ZYD ZYAC. Then the next common byte is ZY. So we replace with W. So WD WAC. Now we do not have any byte pair here. So this will remain as it is. So this is our compressed version. So whenever we need to decode, we will unfold this and we will get this original string. So how we will be using, or we generally use BPE for byte pair encoding for LLM tasks. Actually, we need not have to go into much details of this, but I felt that you should know this algorithm, as already directly tools are available. You can see this tick token tool is available, which uses byte pair encoding to convert this things into labels and tokens and IDs. So here actually, which ensures here BPE ensures that most common words in a vocabulary are represented as a single token. So most commonly appearing words. So there we have seen that the most commonly appearing byte pair have been replaced with some particular symbol which is not appearing, which has not appeared in the text before. So this is what we are following here. So I have one example. I have mentioned here only three to. You can see this. The old is appearing 7 times, older is appearing 3 times, finest is appearing 9 times, and lowest is appearing 4 times here. So while pre-processing or while converting into tokens, basically we will add this end of word token to each word, so that if, let's say, a common string appears at the beginning of the word and the end of the word, we should know that which has to be considered as a token, means ending of the word, so that we can add it as a new token. So here, if we split it into character, let's say that these all words have been split into character. So we get the appearance of characters here. So OLDER, you can see here FINE. So O appears 14 times, L. So basically a frequency of each word that appears here. We can see here. So now next step is to merge this frequently appearing token. token. So if you see this ES part, if you see this ES, so here ES appears like, I can say this 9 times here it is appearing, ES it is 4 times it is appearing, and I think 9, 4, 13, yeah. So 13 times this ES is appearing. So what we will do, we will just combine this ES, okay, and make their corresponding character counts, subtract by these many times the ES is appearing. So S was appearing 13 times. So 13 minus 13 is 0. Similarly for E also. Similarly for E also, I have reduced count to 3. Then we will move next. Then the next common term is EST. So when we go for the EST, so here you can see EST appears 13 times. So the count of ES comes to 0 here. Then count of T is 13. So T has been moved here. So count of T is 0. So likewise, we will try with appearing. Now we will check EST with end of word character. So here also end of word character appearing 13 times. So which makes the count of EST as a 0. And now we can see that there is no other substring which is common to this. So this will survive as 1 token. EST will survive as a 1 token. So here you can see 1 token. Similarly, we will go for old. So we will find OLD as a 1 token. So as I told you that this end of word part, okay, it comes or it helps here where we differentiate between the word that starts and end with the same thing. Like EST comes here also in estimate, and highest comes here also. So from which word to pick the token. So this helps in taking this decision here. Then once we have done with the tokenization, as we have seen this BP algorithm, so algorithm is byte pair key encoding. So next task is to create a input target pair. So this is the last step before the embedding. This is very important because we can see when we are giving input, we cannot randomly give complete input to the text. We need to restrict it to a particular size. So we need to create input target pairs here. So in case of classification and regression, output is very clear. Output we know, but here we don't know the output. Okay, so that mapping has to be done. So what we do is divide the sentence into input and target. Then word after target are masked. As you can see, LLM learns, and then output for this after this is masked, which the LLM doesn't know. Then output of a previous iteration becomes the input of the next iteration. This is the auto regression which I have told you previously, that the output of the previous iteration becomes the input to the next iteration to predict the next word. So here is the simple example I tried to explain, like create input and target pairs. So how can we create the sequence like sequence of this input and target pair? So here you can see, as I said, the input of the previous output of the previous iteration becomes the input of the next iteration. So here you can see the X contains the input tokens and Y contains the target tokens. And here we have mentioned the shift by 1. So here you can see X. If I give 1 as an input, then it will return me 2 as an output. Okay. If I give 1 and 2 as an input, then it will give me 3 as an output. Then if I give 1, 2 and 3 as an input, then it will return 4 as an output. When I give 4 as an 1, 2, 3, 4 as an input, it will return me 5 as an input. So this is nothing but the input target pairs. So how will you like context size? Context size is nothing but this size which I have mentioned, like it is 3 or 4. That how many words you want to give as an input for a model to make a next prediction. Okay. So here the context size is 4. I think everyone is following me till here.
Yes, sir.
So here actually this is one more example I have taken from a screenshot from somewhere. from a paper. So here you can see the sample text. In the heart of the city stood the old library. So here you can see the tensor containing the inputs. You can see in the heart of, and similarly the tensor containing the targets. That is the tensor, the heart of. You can see this. The if I give in as an input, my out model should predict the as an output. Then if I give in the as an input, then it should predict heart as an output. Then in the heart, then out off as an output. So this mapping should be made so that this sequentially on each iteration should be fed to the LLM model for training. Then comes the token embedding. So we have input text, then we have token IDs, and then BP tokenizer. Then these token IDs are converted into token embeddings along with the positional embedding, and then it will be fed to the GPT and LLM model. I forgot to mention here positional encoding embedding. Then conceptual of understanding the tokens embedding. Small hands-on, but I'm not able to share here the screen, so I'm unable to show this. Else it would have been very exciting to show this small hands-on on how this pair is being generated. So why we need embedding? So this is, I think everyone knows, the computer needs numerical representation of a word. So vocabulary, where word and ID is given. But problem with the vocabulary is that it can itself be input to the LLM. But the problem is we cannot relate random numbers directly. Like let's say, as I told you that the in vocabulary words have been sorted in an ascending order, and then the unique ID is assigned to it. But let's say cat comes and kitten comes, so they appears in a different alphabetical order and they have different IDs. So how we are going to relate these two words? There is no way to relate this. Okay, so to relate this, we should have some way to come up to relate to this, that to check whether these two particular words or these two terms have the same meaning or semantic. So for this we go for token or embeddings. So there is one embedding which is one hot encoding, where we just have vectors of 1D vector, where for that particular label, let's say dog, we just make it one there. But this is not going to work. This also has the same problem as vocabulary, or we can say tokenization. It also fails to capture the semantic relationship between the word. So what is the solution for this? The solution for this is vector encoding or token encoding. So we can see here, we can basically see the dimension of a vector is determined by the features. Let's say if I want to convert some terms to the encoding, so what I will do is I will ask some questions related to that, or I will have some parameters which will represent its features. So to the particular word or particular token, if that particular feature matches, then it will have a high value. So for example, I have a feature here has a tail for a dog. So dog has a tail, so it will have a high value for that. Okay. Basically, these values are generated through neural network. So we need not have to go into much details. Already the tools, Google AI, I think have made it available for us. These type of encoding, we can use those encodings directly in our task. But in GPT or LLMs, it actually do not use any predefined these type of encoding. While training GPT or let's say LLM, it generates, or it itself trains for this embeddings and use it in its model. So dog has a tail. So we here you can see this has a tail has a high value. Similarly for apple and banana, you can see is eatable. So they have high value for this, but where has a tail, it has very low value. Okay. So you can see here, basically this is a neural network task, not easy. Usually it is trained on the huge corpus, and these type of I can say embeddings are received from that, and then later we can use it for our task directly. So Google 300 has around, I think, 300 embeddings, 300 embeddings for each words that we can directly use for our task. There was an interesting, there are interesting examples also available using these embeddings. You can directly find context also. Let's say queen plus king, then woman, then question mark. So based on this embedding itself, you can predict that if queen is woman, then king is men. It will directly lead you to the those embeddings. So basically, how to create these token embeddings for LLM. So you can see these embeddings are created by using already existing embedding vectors and the tokens we have. So basically, when we generate this embedding vector, it will be of a particular size, that is the, I can say, vector dimensions into vocabulary size, the number of words we have, okay, and the vector dimensions we have. So that this matrix we will receive for this vector encoding or embedding. Okay, so it's the same thing which I have explained before. Then we comes to the attention mechanism. Attention mechanism, I will go to very basic level, that is the self-simplified attention, because before everyone directly jumps to multi-weight attention, and it is difficult for them to let's say grab this concept of multi-head attention. So we will first start with the attention model, then we will go for simplified self-attention. So as I have a sentence that the cat was sitting on the mat which was next to the dog. Now if I consider that regular embeddings, or let's say regular models which try to predict the sequence, it fails to predict, like or it creates confusion in those models, that whether the cat has jumped or a dog has jumped. Okay, so this confusion is also faced by LLM. So it uses the attention model to pay attention, that it finds out which words in this particular sentence are more close to this cat's action. Okay, so we'll see in the next slide. So there are basically 4 types of attention mechanism. One is self-simplified attention, then self-attention, causal attention, and multi-head attention. So self attention is a forms of basic mechanism for the LLMs, and it has a trainable weights. And difference between self simplified and self attention is it has a trainable weights, and it do not have trainable weights. In the casual attention model, it considers only previous and current input sequence for the prediction. Then the multi-head attention is like if you have a large sentence, and it is difficult for a normal self-attention model to keep track of let's say different parts of the sentence. So multi-head attention, it is a combination of self-attention and causal attention, which basically process the different parts of the sentence with its different heads. So attention model, problem with modeling with long sequence is that we can say any word which has to be translated, it's a language translation task. So where we can say that one sentence has to be translated into a different other sentence. So there is one approach, that is word by word translation. So in that case, the problem is it faces difficulty in case of the sequence, because word by word translation doesn't gives you the details of this grammar and contextual information. So the translated text will be just a direct word level transcription or translation. So the another approach came, which is encoder and decoder based approach, which has a memory model in between. You might have heard the RNN, which we are going to see in the next slide. So it reads and processes the text and generate the context vector. Then this context vector has been given to the decoder, and based on this context vector, decoder will translate the text into the another language. So RNN's most popular encoder decoder based language translation model, which was used before the transformer. So here I have mentioned that input the text, encoder process the input sequentially and update the hidden state here. Okay, and with every iteration or with every word, this hidden state will be updated, and the final state will be given to, which is the equivalent to the memory, will be given to the decoder, and this decoder will generate the final output. So it can be clear from this diagram. So here we can see the German word has been given as input, then the hidden state is updated, this hidden updated state is passed to the next word, du, then this hidden state and on taking MIR it is passed to this. Likewise, when we reach to the final output, final hidden state, this only hidden state is passed to this decoder, and decoder takes this and it generates the output. But the problem with this is all the information is accumulated in the hidden layer, and what happens is it does not work with the long sequence, does not work properly with the long sequence model. So because hidden state, it is only one state, so it cannot retain all the information that has been accumulated for from the longer sentences. So the solution, we can see one paper here I have mentioned in the reference. So that says which was actually the first base paper for the transformer. So it says that let's take the encoder decoder RNN, okay, and selectively access the different part of the input sequence at each decoding steps. So it will help us to decide how much attention has to be given to which token in this sequence. So here you can see, this is the diagram you can see here. So you are processing this or generating this U word from this hidden state. So it has an access to this previous input states, as you can see. So it will help the decoder to decide how much emphasis has been given to these states or these hidden states while generating this word U. Okay, so this is a simple attention mechanism you can see. So as I said, attention mechanism, simplified self-attention, which is without any trainable weights, which I told you in the previous slide. So we can see, given a sentence, your journey starts with one step. So we will focus on the journey. Okay, so how it is related to the other words in the sentences or any existing previous sentences which has appeared long back. So the context plays important role here. So that the attention model will tell that how much attention you should pay to journey while predicting the next word. So this is nothing but take the vector embedding plus the we can say the positional encoding embedding, convert it into the context vector. Context vector plays a very important role here. It is an enriched vector embedding which captures the information that is related to the other words also, means the contextual information also it captures. So this is the paper which I was mentioning. This is not 2024 actually, sorry for this mistake. This is Bahdown attention model, first proposed attention mechanism in this. So here actually how we calculate the context vector. So we have a input vector or token embeddings or vector embeddings along with their positional embeddings. Then we have attention weights associated with each token, as you can see here. And by accumulating these two, we will just perform this, we can say this dot products here. Like A2 will be multiplied with all these units, then A22 will be multiplied with all these units, and finally we will sum them element wise, you can see. So this 0.4 will be summed with 0.5 with 0.5 and 0. So finally we will get this context vector. We will come to that stage also, how we are going to calculate this context vector with an example. So goal of attention is to calculate the context vector Zi for each element Xi. So the context vector in this embedding vector. So now the word under query is X2. So the token which is under observation or which we are focusing on is called as query. So here you can see embedded query token is X2. Here it is journey. So here it is journey. So now journey has its embedded embeddings. Okay, and then we have embeddings for each word. Okay, now how we will come to the attention score, so that the model can decide to what word the importance should be given. So the basic is dot product. We will just dot product them. Okay, and that outcome value will be assigned as a attention score for that particular one. So for this query, we will be getting this as an attention score with respect to each token. So this is what I have explained you with that. So now whatever the let's say if the tokens are similar, if these are the, let's say if the tokens are similar or it has a high relevance with that particular token, then we will get a high value for that. Okay, so you can see here the journey, this is the query journey, and you can see here we are getting high value for that. So now once we got the attention score after the dot product, we will be normalizing it. Why normalization is important? First thing is it is easy to interpret. So we can just simply say, by once we normalize between 0 to 1, we can multiply it by 100, and we can tell it in a percentage way that this particular token has 30% of 30% is 30% important to this particular query token. The main this is just for interpretation purpose, but the main task comes here is training stability in LLMs. Okay, so we have seen that we go even in deep learning also, or in CNNs also, we go for this normalization and all, just for the stability purpose, to avoid overfitting and all. So similar way we use for training stability, we go for this normalization. Now normalization also we perform here in two ways. One is simple normalization and one is softmax normalization. So the simple normalization is just simply we take the score and we divide it by the sum of all the score. So we get this attention weights. So now once we normalize the attention score, we get the new term which are called as attention weights. Remember this term. Then next normalization is softmax way, which manages the extreme value and avoids the numerical instability in dealing with the very large and very small values. So basically it avoids the overflow in the problem. So this is the I can say syntax for, or the formula for this softmax calculation. So this formula which I have mentioned here, it is basically used in PyTorch softmax. So which uses this e raised to power x minus 1. This is raised to power. I forgot to put this symbol there. Minus sum of all these weights divided by sum. So likewise, we do it for all the tokens, and we get this attention weights here. So here you can see why we need to go for this normalization. During back propagation, we can see here, and especially using softmax. Why we use softmax is, so in normalization, during back propagation, even though the value is small, it is very difficult for the algorithm or the optimizer to neglect this. So it assigns some weight to this even values close to 0. Actually, ideally, it should not assign any weights to this. Only it should focus on these relevant values. But the normal or simple normalization fails to do it. So we use this softmax normalization. Sir, I think I'm running out of time. Please let me know if I'm running out of time. Okay, I will wind up there itself. Then comes the attention mechanism, where context journey. So here actually I will show you how this context vector is generated from this input. So we have, let's say we have an input embeddings, vector embeddings, which I told. Then there is an attention weights which we have calculated after normalization. And to get the context vector, which will be used by we can say LLMs for training them. So we will just multiply these two. whatever training weights we have received for a particular query word, whatever attention weights we have received, we will multiply it with individual tokens, whatever tokens are available in that sentence, and the final we will get some value, and we will add that value, and we will get the context vector. So you can, from diagram itself it is clear. So these are multiplied, individual element dot product has been done, not dot product, sorry, simple multiplication, each value is multiplied here, and then whatever output we get from here is simply added. Okay, so we get this context vector. So I think I have finished this. So this was I have planned. I did not go into much details because if attention models are not clear to you, it will be very difficult for you to I can say understand this causal attention model and multi-head attention models. So I think my presentation has cleared you with this attention mechanism, how the attention has been calculated. Okay, so this context vector basically is been used for this prediction of this next word during the training. Okay, so these are the references. These are the major references which I have referred for this. Everyone, I will recommend, if you want to learn about this LLMs, these are the more detailed version of tutorials by Dr. R. Raj Dandekar, who has done his PhD from MIT. Then these are the two base papers which I have referred for preparation of these PPTs. So attention is all you need, and this is the neural machine translation by joining learning, align and translate, which has been published in ICLR 2015. So these are the references. So whenever you are going to learn LLMs, instead of directly jumping to this higher level things, I recommend you to basically clear your basics, such as these type of terms. What is attention, tokenization, how it is performed, how tokenization is passed. Actually, I'm unable to share my screen here, so that's why I was unable to show you how this attention model, with this attention model, how we generate this context vector and how it is used to train the basic, we can say, LLM. But it's okay. I think my time is also up. So if you have any query or something, you can just write me or mail me on my email ID. So I'm writing my email ID here. So I hope it is all visible to gmail.com. So thank you all for having patience during this long lecture. I hope it was useful to you, and thank you all. I will hand over this session to Dr. Raman sir.
Yes, thank you, Pravin sir. Anybody is having any quick questions? Then we'll take maybe one or two only, because time is already up. Sorry, I was audible? Okay, fine.
Someone has written, no sir, thank you so much. It's okay.
Okay.
It's okay.
Okay, thank you, sir. Thank you for highlighting so many things in LLMs, transformers, attention mechanisms, and I think attention mechanisms you explained in detail. And although this is very technical lecture, we got so many things from your lecture now today's, because next 4 days will be on generative AI, and that will be really helpful. Whatever concepts that you have explained today. So thank you very much, sir. And our next session is on artificial neural networks, ANN, and introduction to deep learning by YV Srinivasa Murthy, sir. Vishnu, sir, are you ready?
Yes, sir.
Okay. So I think immediately we'll start the second session. Manoj sir, you have slide of this particular second session.
Hello.
Hello, you have slide to show of the second session.
Yeah.
Okay, please.
Mm, Hello, sir.
You have slide for the second session.
Yes, yes.
Yeah, please.
Just a minute.
Okay. So thank you. So today's second session is Artificial Neural Network and Introduction to Deep Learning by Dr. Y.V. Srinivasa Murthy. First, I welcome Murthy sir, and in brief, I will introduce his biodata. Dr. Vishnu Yarlagada is working at Manipal Institute of Technology, Bengaluru, as an associate professor in the Department of Information and Communication Technology since August 2023. Manipal Institute of Technology is recognized with the status Institute of Eminence by Government of India, procured NRF ranking 6 and in the band of 601 to 800 based on the recent statistics received from Times Higher Education. Prior to that, he worked at various positions in VIT Vellore, NIT Kesaratkal, Geetam University, ANITS, and GEC as well. He received his PhD from NIT Kesaratkal in 2019 as a full-time scholar there. Masters from Geetam University and bachelor degree from uh, Gudlavalleru Engineering College, GEC. And he did his PhD under the supervision of Dr. Shashidhar Kulagudi sir, professor in the Department of Computer Science and Engineering, NIT Kesaratkal. He published around 35 articles in various reputed journals and conferences with H index of 10. One of his articles is published in ACM Computing Surveys, which is ranked A star and produced third rank among all computer science journals with an impact factor of 16. This is very specific. In addition, he has one article in Elsevier Expert Systems with applications with an impact factor of 7. All of his conferences and articles are indexed in Scopus, and a majority of them are flagship conferences with a series greater than 20. Moreover, he published 2 patents and edited one book on malware analysis. He has delivered more than 25 guest lectures on IoT, speech signal processing, medical imaging, machine learning, and cancer guidance talks. He received Best Teacher Award for his excellence in teaching and chosen this profession with passion and working towards it. So, thank you very much for joining here. Thank you, sir. And I hand over the session to Vishnu, sir. Please, Vishnu, sir.
Yes, sir. Sir, thank you so much for your brief introduction, and it's elaborated one. And thank you so much for inviting for this AICTE ATAL workshop as a research person. So today I would like to explain the concepts of ANN. First of all, I'd like to give the complete introduction about ANN and where it will be useful, how it will work, the mathematical background of the particular of the process of constructing the neural network. So let me explain on the whiteboard first. Then I'll go to the PPT. Is it fine?
Yes, sure, sir.
So how many of you are interested to learn the concepts from basic, that means from fundamentals? Can I see some hands over here? Yeah, thank you. So then I'll start the explanation from how ANN has been introduced. So let me connect to my notebook. So hope it is visible, right?
Yes, sir.
Yeah, fine. So thank you, Vanessa, once again, and my good friend also here, Ramu.
Yes, sir.
Welcome.
Yeah. So fine. The introduction of ANN. So let us assume, consider the predictive problems. So first of all, I would like to explain that means how predictive problems will work. So a general standard example I will take. Let us assume that people have started traveling the airline, that means airline services, and one particular airline service wanted to predict how many passengers may travel next month in the particular that organization. So then what they had done is they had taken the data of some um, 10 to 12 years data that they had taken. Then what they have plotted the data in XY plot, where X is time and Y is so number of passengers traveled. So considering they have observed that in certain months the number of passengers traveled in that particular airline services are high, and at particular time the number of passengers traveled in that particular airline services are low. So then so based on that one, they had drawn this kind of graph. That means they have plotted XY, where x-axis is time and y-axis is passengers. Now they wanted to predict the next, how many passengers may travel in the next month or next 2 months. So they wanted to predict it. Generally these kind of problems can be we can call it as regression problems. And if it is linear problems, then they can be solved by using y equal to mx plus c, where m will be called as intercept or slope. So slope, c will be called as intercept, and x is the present sample, present data, and they want to predict y, that is future data. So that means now based on this particular, so based on this particular formula, they tried to introduce simple linear regression formula. This is simple linear regression formula, and they wanted to predict the future data. Later on, what they had done is they have expanded, that means they have expanded this particular formula. They wanted to identify the y cap, that means predictor. They want to predict the future, and um, based on the previous values like m1 y1 plus m2 y2 plus m3 y3 and so on, m4 y4 plus epsilon. So what are these values in the sense? I want to predict the future values. So the previous sample may not be sufficient. The previous sample, that means suppose if I want to predict this particular value, this particular previous sample may not be sufficient. What they can do is they can take the previous some n samples. So previous n samples will be considered, and so relevant weights also they will enter. That means this m1, m2, m3 will be the weights. So this is called as weighted moving average method. Initial simple moving average method they had taken, then they had gone for the weighted moving average, where epsilon will be considered as error. So where this epsilon is equivalent to y cap minus this m1 y1 plus m2 y2 plus and so on. That means y cap minus y will be considered as epsilon. My error is equivalent to y cap minus y, where all this part will be considered as y. That means this is actual value, where y is an actual value and y cap is a predicted value. The difference between the predicted value minus actual value will be the error. So soon, later on, what they understood is sometimes the error may be positive and sometimes the error may be negative. That means they can see both kind of errors, positive errors and negative errors. In case of predicting this particular value, they may get error E1. While predicting this particular value, they may get error E2. To predict this particular sample, they may get error E3 and so on, error E4 and so on. Now, whenever they are finding the sum of the errors, what is the total error for predicting the next 2 months values, 2 months samples? If they want to find the sum of all these errors, so because of this positive and negative, so they may get some error in error, what we can say. So it is not a correct way of finding the error. Then what they introduced is they have identified the absolute of these values. That means they introduced they have introduced the absolute terminology for this part, finding the errors, as well as some places mostly people use squared errors. So this way they identified the error. So now one can imagine there is XY plane where the present data is available and they wanted to predict the next data. In order to predict the next data, they are using the linear regression formula. That is, initially it is y equal to m plus c. Later on it has been expanded. Now consider this y equal to m plus c as y equal to wx plus p, where w is a weight and b will be considered as bias and x is the previous sample value. So if it is expanded, then y, so now if I draw the representation for this, how it looks like, I'm going to compute y. This y will come based on the, summation of x into w plus bias. Now, so this will be the representation of this particular equation. This equation, you can imagine that this is a weighted sum of wx plus b will be giving the y. Now, later on what they had done is y equal to w1 x1 plus w2 x2 plus w3 x3 plus and so on wn plus xn plus bias b. So yeah, fine. So then how this representation can be, how we can represent this particular formula in the sense, so we have summation where the inputs will be x1 w1 x2 w2 x3 w3 and x4 w4 x5 sorry xn wn. Yeah, this way they had started representing. That means the y will be, this is y cap. Y cap is equivalent to, based on the summation of x1 into w1, x2 into w2, x3 into w3, x4 into w4 and so on, xn into wn plus bias value. Now what will happen? How to choose these w's is the question. How to choose these w's is the question. So now they have introduced the concept called as randomized. These w's can be chosen based on the random values. Okay, now if I apply the random values to these W's, and for these given inputs, that means x1 into w1, that means what I can say that this matrix will be x1, x2, x3 and so on xn. This is a n by 1 matrix, and the next one is w1, w2, w3 and so on wn. It will be 1 by n matrix. If you multiply, I can reverse it, sorry. Yeah, fine. So this x1, x2, x1, x2 and so on xn will be the matrix of size 1 by n. Yeah, I think previous one is correct. Yeah, x1, x2 and so on xn, it is 1 by n, and this w1, w2 and so on wn, it will be n by 1. So now if you multiply these two matrices, the dimensions 1 by n will be multiplied with n by 1. You will get a matrix of size 1 by 1. So that will be added to the bias. You will get y cap. Fine. So this way we can find. But whatever the values that we considered for this particular weights are random. Then what people have done is they have performed some analysis or some research on our human brain, that means human nervous system, how neurons of the human being will be connected, and how they will activate, that means how they will remember the data, how they will think. All those analysis have been done. Now based on that one, they assumed that okay, initially these weights are random values. Even after multiplication of these two matrices, I'll get some value which may not be satisfying the y cap, which may not be satisfying the user predicted value. What we can do is we can perform some back propagation. So come back. So suppose if you're getting what you can do is you can find an error. The error is equivalent to, as I mentioned, that y cap minus y whole square, or y minus y cap whole square, whatever it may be. Target value minus predicted value whole square, y minus y cap whole square, whatever it may be. Anything is fine since we are finding the whole square. So after finding this error, with respect to error, they want to adjust the weights. Though weights divided by dou e. The difference between the actual value and predicted value. So they wanted to identify and they wanted to adjust the weights according to the difference observed. Fine. Now you will get the new weights and perform the multiplication again. Next time you may get the different error. So likewise, see, initially your error might be at this particular state. Next time whenever predicting, your error may be at this stage. Sir.
Sorry, sir.
Yeah, sorry. Next time whenever you are predicting, your error may be at this place. Next time whenever you are predicting, your error may be at this stage. So that means you are moving like this. Assume that. Next time whenever you're doing the back propagation, your error may be little reduced. Next time it may be little reduced. Next time at this place. Next time at this place. Slowly your error is getting reduced like this. Assume that it will. Now this process is gradient descent. At certain stage, your error will be converged. That means your error will reach to the saturation stage. That means from that particular stage, it won't modify that. It will be converged state. So this will be called as gradient descent. So this will be the origin for the neural networks. The origin, I had taken a simple example. It can be anything. See, suppose if I'm having a bakery, if I don't prepare a maximum number of cakes on December 31st or January 1st or December 25th on New Year Day. So on these days, if I'm not preparing, otherwise, if I'm not preparing more number of cakes in my bakery, that means I'm not a good businessman. Similarly, if I'm having a textile industry, so that means during festival seasons like Pongal season, or it can be Yugadi, or it can be Deepavali, or it can be Dasra. So during these days, if I don't maintain the good stock, so then I'm not a good businessman. Similarly, whenever festival seasons comes, if I don't keep offers in the Amazon, and if I don't know how many orders will come, that means if I don't keep the uh, relevant products in my Amazon store, I'm not a good businessman. So all these are for business intelligence through machine intelligence. So they have started with the time series data initially for predictive analytics. So they have taken some data sets. Like tomorrow, I'll give the hands-on with these data sets. Today also, I'll give representation of these data sets, how it will work. Fine. Yeah. So then they started predicting the next values based on the previous values. Then they have introduced the linear regression formula. So once linear regression formula is there, then it will work only with previous sample. Now they want to increase the number of samples. That means based on the previous n samples, they want to predict the next values. Then they have enhanced the regression function. So that regression function can be represented in this form. So if it is represented in this form, then the next thing is if there are more number of inputs, these inputs now it will be features. Features are previous values. That means I'm going if n value equal to 10, based on the previous 10 values, I'm going to predict the next value. Like that they have identified. Then they have observed this particular formula, that is multiplication of two matrices, where the first matrix is of 1 by n and second matrix is of n by 1. If you multiply them, you'll be getting 1 by 1, that is one value. It will be multiplied with bias, where this bias also is a random value. So now they started performing the back propagation to adjust the weights by using this partial differentiation. How much difference is there from the original value to the predicted value? Then they started adjusting the weights and tried to predict the value again. So finally, they will get different errors. The errors can be represented in the graph like this. If you represent, you'll get this kind of cup shape. This cup shape will be called as gradient descent. Initially, your error may be high. Finally, your error will be converged, but not immediately. It will take these many iterations. Later, people have performed some operations to reduce this number of iterations. I want to quick. I don't want to take these many steps. Just I want to perform. Simple. So is this possible? Also, people are doing research now. Still, there is a lot of scope for all these things. So this is the origin for back propagation. Now I'll show some PPTs and I'll come back and I'll explain the concept of proper neural network with one example, how it will work step by step. We shall see. Can I proceed like this? Is it fine? Or is it too much basic?
Yes, sir.
Is it fine? Yeah.
Yes, sir.
Yeah, fine. Thank you. Thank you, Krishna sir. Fine. My other screen is visible. It's visible, right? Yeah. So welcome to a 6-day AICTE online ATAL FDP. So organized by Yashwant Rao, Bonsal Institute of Technology. So Here I started with the basic fundamentals of ANN, how it will work. So this is my complete presentation outline. So apart from the explanation that I had given on the board, so I would like to explain the basic regression problem and the regression problem example, introduction to neurons, the structure of biological neuron, how it will be converted to artificial neuron. So then the next part is the feed forward neural networks. So then next part is backpropagation with some sample code. So these are the three pioneers of artificial neural networks: Warren McCulloch, Walter Pitts, and Frank. So we have to remember them whenever we have to learn about the artificial neural networks. Because of artificial neural networks, nowadays people are stopped the thinking, stop the process of thinking. Am I right or not? Of course, yes. So no one is interested to think nowadays. So because we have ChatGPT, it will give the solution for every problem. Even if you think anything, it is giving the solution. If you want me, I can give the example also for that. Anyways, that is later part. As I specified that the problem has been started with predicting the values time series data. So for this purpose, I have plotted the data from 1948 to 1948 to 1949 to 1961. 1949 January 1st to 19 sorry, yeah, given I had given values here. 1949 January 1st, 112 passengers have been traveled in that particular airline. 1949 August, 148 passengers have been traveled. Then similarly, 1960 December, 432 passengers. That is the number of passengers traveled in that particular airline company have been increased in a upward trending. If you draw the same thing, yeah, I had drawn the upward trending. So this is the way of now how many passengers may travel in the next month. So what I had taken initially is I had taken the 12-month average. This 12 months, this red line indicating that it is a 12-month average. Okay, so this 12-month average I have plotted for the given data. So since first 12 months there won't be any, first 11 months there won't be any average. First 12 months have been first 12 months average has been plotted on the 12th month. Then you can see this is the red line. So it is towards upward trend. I had taken the simple moving average method here. So where this red line coefficient is 2.66, that is slope, and intercept value is 70.189. I have converted this to weight and this to bias in our diagram. So the slope is converted to weight and the intercept is converted to bias. The next month index, that means the number of passengers travel in the next month will be 456.833. This is the predicted moving average. That means I have specified that there will be 456 passengers may travel in the next month. This is a simple linear regression formula where slope can be identified by using n sigma xy. X is a sum of sample, that means x into y has been done, and the sum of samples will, the summation of x into y, and yeah, minus sigma x into sigma y divided by n into sigma x square minus sigma x whole square. This is the formula to identify the slope in a simple linear regression model. And intercept has been calculated by using the sigma y minus m into sigma x divided by n. So this is the way of finding the slope and intercept. So this is the basic formulation for the neural network. This will be the base for the neural network, what I can say. So the representation of equation in the form of diagram, you can see yi is equal into beta naught, where beta naught is a intercept or constant, we can say, or bias in our neural network terms, plus beta 1, where beta 1 is represented by using the slope or coefficient or weight in our neural network terms, where xi is a previous term and yi is a next term, yi is depending on xi, where xi is independent term, or we can call it as a feature. All features are independent variables, and all target variables are dependent variables. The same thing I have mentioned here. Now, this representation, you can imagine, you can say this beta naught will be the weight one, W1, and this xi, x1 independent variable will be input layer, input to the input neuron, and B naught will be the bias, and the sigma will be done, that is Wx plus B will be done, that Z is equivalent to Wx plus B. We have to activate, that means we have to convert it into normalized formation, that means either 0 to 1 or -1 to 1, or we have to convert it into that particular format. Normalization has to be done for the summation. For that purpose, there will be activation function. Here I had taken the sigmoid activation function. One must know what is the sigmoid activation function. That is a 1 by 1 plus e power minus lambda. That means e power minus z here. Now the neuron gets activated and we'll get the predicted value. This y dash may not be equivalent to ya, actual value. So that will be considered as error. So how it has been increased? See, how it has been enhanced from the simple linear regression formula. The simple linear regression formula is y equal to beta naught plus beta 1 into x1, where beta 1 is slope and beta naught is intercept, plus epsilon, where epsilon is an error. We can say that now epsilon is equivalent to beta naught plus beta 1 x1 minus y minus beta naught plus beta 1 x1, where y is the actual value, beta naught plus beta 1 x1 is a predicted value. So this is yi. So this y minus yi will be the y minus yi will be the error. So generally we will compute the whole square of it. Yeah, fine. I don't want to take much time. So another 10 or 15 minutes, I'll try to finish this particular slide, because another half an hour, I want to explain the backpropagation process. And last part, I would like to explain the coding hands-on session as well. Tomorrow will be the complete, next session will be the complete hands-on with CNN. Anyways, fine. So the next part is multiple linear regression. So one variable, one independent variable or one feature may not be sufficient. For instance, if I want to predict the next price, the price of the car, suppose if I want to sell my car, if I have purchased the car today, if I want to sell after 2 months, then the age is only 2 months of for that particular car, and I had driven some 1,000 kilometers, assume that I'll get some price. That means next time, after 1 year, if I want to sell my car, then age will become 1 year, and the mileage of the car might be 10,000 kilometers driven. So the car price will be different. So that means the price of the car may not be depending on only age, or may not be depending on only mileage. Suppose if the car mileage is some 80,000 kilometers, I want to purchase this car, but that car has been driven 80,000 kilometers in 2 years. That means the car has been rigorously used. So I cannot take such kind of cars, because the body parts might have shaken because of this, might have got damaged also, the mechanical parts. So age cannot be the only factor that decides the price of the car, or mileage cannot be the only factor that can decide the price of the car. So using these two factors, we can say that the price of the car will be the so and so. Then people had gone for the multiple linear regression. So y equal to beta naught will be the always bias, or we can call it as a intercept, plus beta 1 x1 plus beta 2 x2, and we may get some error. Again, this complete part will be the y cap. So y minus y cap will be the error value. So simple, same. So the example that I taken, y equal to price, beta naught intercept, and x1 is age and x2 is mileage. The features are increasing now. So the same thing I have plotted. So age versus price. How it looks like. if the car age is 1 year, and if I consider only age, 1 year, 2 years, 3 years, 4 years, 5 years. If I consider a price based on age only, it is the value is getting deteriorated. We can appreciate, but we cannot depend on only age. So if you depend on only age, it will be simple linear regression. Now, see multiple linear regression. So the first side, if you see age, what could be the price of the car? Mileage, what could be the price of the car? Oh, 1 second. Fine. Yeah. So age versus price, and second one is age versus price, and mileage versus price. That means we cannot depend on age to predict the price of the car, and the mileage to predict the price of the car. So the combination of these two things will be the multiple linear regression. How it looks like in the sense, price is equivalent to 32.46. 32.46 is the intercept value, minus 1.54 is the slope for age, and 0.23 is the slope for mileage. So that means if age is equivalent to 2 and the mileage is equivalent to 50,000 miles, someone has turned on Komal ma'am. Ma'am, can you turn off your mic? Yeah, fine. Thank you, ma'am. Komal ma'am. Komal sir or Komal ma'am? I don't know. Fine. Yeah. So price is equivalent to 32.46 minus 1.54 into 2 minus 0.23 into 50. That is 21.88 kilo euros. That means we can say that it is around 21,000 euros. The car price will be. So this way multiple linear regression has been introduced. So this can be applied to the next thing. So the blood pressure, SBP, blood pressure value, and age in years. So gender, man or woman, we can classify them as man or woman. So simple data set I had taken here. So I have plotted SBP as well as age here, SBP over age. So then I have constructed the linear regression. So we can see the proper discrimination over here. That means we can see the linear discrimination where the classes can be properly categorized, men and women. So here I would like to specify the same thing. I have plotted age versus SBP, age over SBP. Then after seeing the data, one can say that there can be a proper discrimination like this. So where it can be classified into men as well as women. So the another example for the multilinear classification that I had taken is sea bass and salmon fish. There are two species of fishes that looks like this. These two fishes can be classified. That means one can say based on the parameters. So when you are seeing the sea bass, the lightness is high. When you are seeing the salmon fish, the lightness is low. The width of the sea bass is more and the width of the salmon fish is less. So this is also a multilinear regression problem. So it is having two parameters, x1 and x2. We can take two weights, w1 and w2. w1 x1 into plus w2 x2 plus bias will give the predictor value. If you have to identify the w1, w2 and bias. So one can see the sea bass and salmon data set. So the prerequisite for machine learning will be always the data exploration techniques. That means one should know how to analyze the data. I have plotted the PDF for CBUS and Salman, considering this is X1 values, PDF for X1, and this is for PDF for X2. One can see the overlap is very low in this when I have plotted X1 over X2. Here in this case, the overlapping is more. That means one feature may not be sufficient to categorize the fish into Seabass and Salmon. We need two different features that have been considered here. So once if I plot the lightness over width for Seabass and Salmon, one can observe there is a one can observe there is a linear discrimination. Very less values have been misclassified as Salmon, though they are Seabass, and very less values have been misclassified as Salmon, though they are misclassified as Seabass, though they are Salmon. So likewise, one can draw the linear line. These are the basic data sets. Fine, one can easily draw the linear line for these kind of data sets. But whenever if you come to the real world environment or real time applications, the data will be not normal. So one needs a classifier that can classify the data, though it is a. So we need this kind of classifier that can properly discriminate Seabass and Salmon and completely non-linear. So linear of degree 1 only, polynomial of degree 1, but we need a polynomial of degree 4, 5, 6. So Pravin sir might have explained that random forest and all those things. So random forest and SVM, how the SVM kernel will be useful to draw the non-linear patterns. So we need a proper classifier. The proper non-linear classifier that we have found from human being itself. Whatever the computer applications that we are developing is based on the human behavior. Completely based on the human behavior. How we think, how we walk, how we behave, how we analyze. The same way system is behaving. But system is quite faster when compared to the human brain, since it contains electrons. So fine. Now you can see this biological neuron. A biological neuron, the structure of the biological neuron will be like this. It will be having the important organs like axon, dendritic branches, and nucleus, axon, cell body. So these are some important terminology. And from this biological neuron, people have started constructing the artificial neuron. So this biological neuron will be will be transferring the values from these dendrites. These dendrites, they are considered as inputs. And this cell body, they are considered as for summation and activation function. And this axon will be the output, and it will be connected to the terminals. Axon will be the activation function. So this formation has been done. Whatever the diagram that I explained on whiteboard, the same diagram has been represented over here. So the same thing. So the inputs will be x1, x2 up to so on xn, w1, w2, wn. Fine. I'm going to find the summation. That means summation of xi and xi wi plus bias. So this will be the z. That means x1 w1 plus x2 w2 plus bias will be the z. Then we are giving it to the activation function. The activation functions, we have tan h sigmoid activation function. This is basic this is tan h activation function. We'll consider the values from -1 to 1. So and it will give the output. So you can see how the human neuron is there, and well, so this neural millions of neurons have been trained recurrently or repeatedly, and it became like ChatGPT after some days. nothing else in ChatGPT. See, a representation of ANN for any data set. Let us assume that my data set is contains 395 samples. The data set representation will be in the form of this always. It's a matrix. Contains the rows. Rows will be called as samples. Also contains the columns. Columns will be divided into two parts. One is independent. One set is independent variable, and the other set is dependent variables. Dependent variables will be called as target variables, where independent variables will be called as features. We can call them as features as well. So this data set is containing 3 features and 1 target variable, as well as 395 samples are there. 395 samples. Since 3 features are there, so the input of the neural network will be having 3. It will be connected to the hidden neuron. Why it is connected to the hidden neuron is for improving the performance of the system. The number of hidden neurons also matters. Sometimes the usage of more number of hidden neurons will lead to the overfitting. Overfitting is nothing but though the class is not a particular class, it is classified into the particular same class. It is classified. So then these will be considered as hidden layers. Hidden layer here, hidden layer contains 4 neurons, and finally it is connected to one output. So it is a binary classifier. It will say either yes or no, or it can be connected to multi-classifier, the multiple outputs also. Suppose if I want to classify the given input as 0, 1, 2, 3, 4, 5, like that. So that is also possible. Fine. This is the basic structure. Come back to the whiteboard. Then I'll explain the basic structure with an example. I'll perform the forward propagation and I'll come back to the back propagation in detail. So I have explanation with the complete back propagation with mathematical analysis. To give this, first of all, I have to explain all these things on the whiteboard. So can I explain on the whiteboard? I'll go with the PPT directly. Can anyone respond through chat or anything? Okay, PPT. Directly I can go with the PPT. Yes, fine. So then open in GoodNotes. Yeah, fine. I'll go with the PPT as mentioned by the listeners. So I hope it is visible. Yes, sir. Thank you so much. Yeah. So let me create a new page after this. Yeah, fine. So now see, the architecture of the neural network will be like this. Previously, we had seen no hidden layers. Now hidden layer concept had come. Once hidden layer concept had come, the complexity of the function also gets increased. Now let us assume that this is input and this is a hidden layer H1, H2, H3, and this is a W1, 1, W12, W13, W21, W22, W23. What it indicates that Wij is nothing but weight from ith input variable to the jth hidden neuron. So this way it is represented. Fine. Similarly, this matrix I'll consider as V1, 1, V21, V31, and this is my output. So here B1 will be connected, B2, B3, B11, B. I can say that B12. Otherwise B11, B11, B21 or B31. So here also bias, that is B11. Each neuron will be having its own activation function. The sigmoidal activation function is equivalent to 1 by 1 plus e power minus z, where z is equivalent to sigma xi wi plus bi bias. Now consider this. The matrix will be x1, x2, x3. This is 1 by 3 matrix. Now it will be connected to W11, W12, W. I can say that 13. Similarly, W21, W22, W23, W31, W32, W33 plus B11, B21, B31. This 1 by 3 matrix will be multiplied with 3 by 3 matrix and will be further it will be added to the bias. I can take it like this also. What is there in that? B11, B21, B31. So the multiplication of these two, 1 by 3 into 3 by 3 will result into 1 by 3 matrix plus 1 by 3 matrix. So we'll get some 1 by 3 as an output. Now, whenever you are multiplying, x1 will be multiplied with the W11, where x2 will be should be multiplied, where x1 should be multiplied with W. I can say that, yeah, here only two values are there, right? Why I had taken three values? Sorry, I'm assuming that one more input is there. So let me erase it. Yeah, fine. x1, x2. It is only 1 by 2 matrix. This will be W11, W12, W13, W21, W22, W23. This is 2 by 3. Yeah. Now x1 is multiplied with W11 and x2 will be multiplied with W21. Same thing, right? X1 into W11 plus x2 into W21 will be the. So similarly, x1 will be multiplied with the W12, x2 will be multiplied with W22. So x1 is multiplied with the W12 and x2 is multiplied with W22. So this will be the input for the hidden neuron 2. Now similarly, x1 is multiplied with the W13, x2 is multiplied with W23. So W13, x2 is multiplied with W23. So this is input to the neuron. So this way the multiplication will happen and you will get 1 by 3 matrix. The resultant will be 1 by 3 matrix. This will be added to the B1, B2, B3. This is also 1 by 3. So the summation of these two matrices will give the result. So that means it is summation of xw plus bias. That is y cap. So we are satisfying the condition. So now to move from this particular input to output, we have to apply this activation function for each neuron because it will normalize the values to 0 to 1. It will smoothen the values, we can see. Now after that, we got H1, H2, H3. So then they have to be multiplied with V11, V21, V31. So that means H1, H2, H3 should be multiplied with what I can say 3 by 1. V1, V2, V3. This is 3 by 1 and this is 1 by 3. We have to reverse it. Yeah, we have H1, H2, H3. This is 1 by 3. And we have V1, V2, V3. V11, V21, V31. This is 3 by 1. So now 1 by 3 is multiplied with 3 by 1. You will get 1 by 1 value. That means single value plus one single bias will be the input to the output layer. Now this input to the output layer will be given to the activation function again. You will get the output. This is a predicted output. We can say it as a y cap, but y cap is not equal to y. There will be error. That is y is equivalent to y minus y cap whole square. Sorry, it's not y. This is error is equivalent to. Error is equivalent to y minus y cap whole square. Now imagine your data set is having some 10 samples. Or 6 samples. 2 features. When I passed the first feature, I got E1. When I passed the second feature, I got E2, where E1 is equivalent to y1 minus y cap, y1 cap whole square. Okay. So when I passed the third feature, I got E3. When I passed fourth feature, I got E4. When I passed fifth feature, I got E5. When I passed sixth feature, I got E6. The summation of all these things will be EI for I equal to 1 to n. And I'll find the 1 by 2m, the number of samples. This will be called as mean square error of one epoch. Mean of all these values of one epoch. So if we elaborate this one, 1 by 2m sigma I equal to 1 to n yi minus yi cap whole square. Now this mean square error will be plotted on the graph. First mean square error will be here, second mean square, third mean square, fourth mean square, and fifth mean square. If you get it in 5 iterations, it will be good, but it will take 1000 iterations. We can say this one mean square error is one. All these iterations can be one epoch. All these iterations can be one epoch. Likewise, we have to run that algorithm for 1000 epochs, 10,000 epochs. Then you can find the converged errors. Converged weights can be found. This is the theory behind backpropagation. The same thing has been explained here. The backpropagation has been started from the linear function x and f of x had come. So if you want to predict the new values, if the predicted value is here and previous value is here, and you have to find the difference between these two, that will be done by using x plus delta x. X is here, original x, and there is a predicted value that is x plus delta x. X plus delta x minus x is the important thing that we have to find, but in space we cannot find the difference directly. We have to go for the differentiation functions. That's why the difference, because of this, the partial differentiation had come into picture. That has been explained in the initial slides with too much mathematics, which is not required. We shall start the process from this particular location. Yes. Till now, am I fine? Is it fine? Am I making sense over here? Is it fine? Some responses from audience.
Yes, sir. Yes, sir.
Thank you. Thank you.
Yes,
so much,
sir.
Fine, sir. Thank you so much. So now, in this particular example, there are three features are there, 3 independent variables, and there are 3 hidden neurons, and there are 3 output. That means 3 classes of outputs: class 1, class 2, class 3. Let us assume that. So class 1, class 2, class 3. So this is the sample neural network, where the terminology E stands for error, EK stands for error at the kth neuron, TK stands for target output of class K, OOK stands for output of the kth neuron, IOK stands for input to the kth neuron, OH stands for output of the hidden neuron, OIH stands for input to the hidden neuron. So all these things are references from the Rajshekhar Pai book. Rajshekhar and Pai are 2 authors of that particular book, Genetic Algorithms and Fuzzy Systems. So this is the representation of gradient descent. Initially the error is here, next the error will come here, next it may reach to here, or it may reach to here, or it may reach to here, or it may reach to here, any place, so which will form a cup. So this representation will be the gradient descent, as I explained. I'll share all these slides with you. So fine. Yeah, I started with an example here. I'll go to the direct example since still I think we have 20 minutes left. I'll directly go to the example. Yeah. Let us consider x1, we have input 1, x2, we have, and y, that is target variable. These two are independent variables. This is a dependent variable. And we have to predict y based on the x1 and x2. So our neural network will be having two inputs, one hidden layer with the two neurons. You can put it to 3 also. For example, I had taken like this. So the terminology, input to the input neuron, xi, that sample variable, input to the hidden neuron, output of the hidden neuron, input to the output neuron, output to the output neuron. Okay, this is the terminology followed by me. But fine. So the input is, the first sample that I had taken is 0.4 and minus 0.7. So that is input is 0.4 and minus 0.7. The random weights that I considered here is, this is V and this is W matrix. So this particular representation is considered as V and this representation is considered as W in this particular example. So 0, 1.4 minus 0.2, 0.2 will be the V, and 0.2 minus 0.5 will be the W. These are the initial random values considered. So what I had done is, I can do the transpose to the input neuron, or I can take the transpose to the weight matrix. So I had taken the transpose to the weight matrix. The size of the weight matrix is 2 by 2, and the size of the input matrix is 2 by 1. So now I have performed the multiplication among V transpose into this particular part, that means 0.4 and minus 0.7. Then V transpose into 0.4 and minus 0.7. I got this value. That means these are the input for the hidden neurons, 0.18 and 0.02. The output of the hidden neuron will be the activation function. That means we have to activate these neurons. This is 1 by 1 plus minus 1 by 1 plus e power minus 0.18, 1 by 1 plus e power minus 0.02 will be the, I have performed the sigmoid activation function here, and I got 0.5448. So that means this is 0.5448 and this is 0.505. So this is multiplied further. This will be multiplied with the W transpose I had done. Then 0.2 minus 0.5 is converted into horizontal. That means 2 by 1 matrix is converted into 1 by 2 matrix, and it is multiplied with the 2 by 1 matrix. So the 1 by 2 into 2 by 1, the output come of the matrix is 1 by 1. So this is the output that I got. Again, this is the input of the output neuron. Now it has to be passed through the activation function. So sigmoid. So the final output that I got is 0.4642. Actual output is 0.1. This is my Y and this is my Y cap. So I got Y cap here. So 0.1 minus 0.4642 whole square. What is that? That is target output minus, sorry, actual output minus calculated output. Whole square will be the 0.13264. That is my error. Am I clear till now? Okay, fine. Now I got the output. Then I have to perform the back propagation. How I'll perform the back propagation? The back propagation is error identified at the output stage with respect to the output of the output neuron, and with respect to the input of the output neuron, with respect to the output of the output hidden layer, with respect to the input of the hidden neuron, with respect to the input. So this much of back propagation, child multiplication has to be done. That means though error with respect to the output of the output neuron into though output of the output neuron with respect to the input of the input neuron into error identified at the input of the input neuron. Yeah, simple. Yes, correct, sir. Mahendra, sir. So error identified the input of the output neuron with respect to the output of the hidden layer. So it's a chained multiplication, chained back propagation, or chained partial differentiation. So we'll get the new weights here. The difference in weights. By using the difference in weights, we can compute the new weights. So now the same thing has been done here. So delta, that means the new weight, the next weight will be next W and next V we have to compute. The next weight will be the eta. This is called as learning factor. The value will be 0.1 to 0.021. Mostly learning factor will be high always. The people will take 0.8 or 0.7. for better there is a better practice based on the experiments conducted. So OH into D, that is a formula identified after performing the differentiation. So where output of the hidden layer, we know it, where D is equivalent to target variable minus predicted output into predicted output into 1 minus O. Okay. So this formula will give the difference in weights. This is a difference in weight. Now, previous weight plus difference in weight will give the next weight. So that is the process followed here. So we know that 0.1 is the target variable. Output is actual output. Computed output is 0.4642. Output of the hidden layer is 0.5448 and 0.505 we got. With that, D has been computed. The D value is minus 0.09058. So then after finding the D value, we have computed the next weights. Next weights value will be these things by using the alpha and eta factors. So that means previously the weight values are 0.2 and minus 0.5. It has been 0.2 and minus 0.5 has given some X error. To reduce this X error, we have to upgrade it to the new weights, that is minus 0.02958 minus 0.02742. There is no guarantee that these weights will improve the performance. It may give the different error. So likewise, slowly we are learning. In childhood age, if I had given A like this, then you will start writing A on this for 10 times, 15 times, 20 times. Later, if I ask you to write yeah, it is delta W. No, sorry, it's not new weights. Thanks, correct. This is delta W. W plus delta W will be the new weight. Thank you, sir. Yeah, so we will write A on this particular part. If I ask you to write A, then some people will write A like this. Some will write A. That means our neuron system is not completely learning. But once if they learn, they will write like this. At the same time, if you see the children, they will be very enthusiastic. If they see A on the boards and flyers or placards, anywhere, if they see, Mommy A, Daddy A. So that means similarly, neural network, that since we are designing the neural network to slowly learn it, so it may not write the proper A based on the learning process at this first stage itself. Yeah, as I explained, so we can compute the new weight as W plus delta W, as Sir has quoted in the message. Similarly, we'll do the operation for finding the delta V. So where the new weights will be, the next weight will be the previous V plus delta V, and the next W will be the previous weight plus delta W. So this matrix will be considered for next iteration as V, and this matrix will be considered for the next iteration as W. Now we got E1. With this new matrices, we'll pass the second, not the first one. We'll pass the second sample. We got E1 here. Similarly, we'll get E2 and we'll get new weights. We'll pass third sample. We'll get E3, E4, E5. So we'll find the mean square error of all these things. 1 by m sigma ei square will give the mean square error. That is one epoch. Likewise, if you iterate this particular algorithm for some 500 epochs, then you will get minimum error. So weights will be converged. There won't be any change in the weights. Is it making sense? So this is what I have planned for the today's session, the incomplete fundamentals of artificial neural networks. And introduction to deep learning also I have to give. Sorry, where I'm going. New page, sorry, here. Yeah. Now introduction to deep learning. Assume that the features are the number of dimensionality vector is high. Assume that the number of hidden layers used in the first hidden neuron is some 64. Second layer, some 32. Third layer, it is 128. Then fourth layer, 16. Fifth layer, 2. And this is my softmax function. Now, the number of inputs are 56. Assume that. Now, what is the dimensionality of this particular matrix at this stage? 56 by 64. The dimensionality of the matrix at this stage is 64 by 32. Okay, and at this stage it is, I can say 1 by 56. At this stage it will be 32 by 128. At this stage it will be 128 by 16. At this stage it will be 16 by 2. So these are the matrices. That means now, sorry, 1 by 56 into 56 by 64 into 64 by 32 into 32 by 128 into 128 by 16 into 16 by 2. Multiplying these many huge matrices needs high computational power, and generating these many random weights and performing the back propagation and adjusting these weights. Imagine a big network, and if the sizes are increasing, if the number of hidden neurons are increasing, then it will be a big network called as deep neural network. Where ordinary process is sufficient, ordinary processor is sufficient, or ordinary CPU is sufficient to execute a normal neural network. But we need a processor with high computational power is required to execute these kind of deep architectures. So that's why there is an intervention of HPC, stands for high performance computing. So people have tried to increase the RAM size, processor, the number of cores in the processor, and tried to introduce master slave CUDA programming to perform the parallel computation. And master slave Hadoop networking is there to establish the master slave network. GPUs have been introduced for performing the parallel operations with graphical processing units. So this is the deep neural network. So this is about today's session, and the next session I have planned for introduction to CNNs in the similar way. Also, I'll give some hands-on. So I'll take half an hour only in the next session, and remaining 1 hour will be the hands-on, completely hands-on. I'll explain how to see the image clearly and how to perform the convolution operation at each stage, and finally how to give it to the neural network. And the neural network code also I'll explain one sample code how it will work on this Thursday class, Thursday evening session. That is my second part. Is it fine? So this is what I had thought in this particular presentation, and rest 5 minutes will be the question and answers. If you construct a deep learning is nothing but a neural network with high number of hidden layers will be the deep neural network. That deep neural network will be used to understand the problem deeply. The complex patterns in the image are the complex patterns in a signal, are the complex patterns in a data simply. Yes, sir. Of course, if we have proper idea in the mathematics. So till now, the data will be in the form of 0 to 1 or -1 to 1. So whatever the activation functions that are there, since we are normalizing the data to either -1 to 1 or 0 to 1, the present activation functions are sufficient to smooth the for smoothening. That is tan h and activation function and ReLU function, that is rectified linear unit. So ReLU has solved all the problems. In most of the convolution process and deep learning architectures, people have used ReLU only, except at the softmax stage. Softmax stage, again, we have to convert it into 0, 1, 0 to 1 or -1 to 1. There we have to use sigmoid or tan h. Nearest weights, that is up to you, sir. The weights that you have chosen can be randomized. As of now, there is no since we cannot predict what is the pattern of data, it is very difficult to estimate the weight values. Some more questions. Yes, sir. Based on the number of layers and number of neurons in each layer, we can.
Any more questions, please?
Can I get some 1 or 2 feedback? That means is a what is the activation function for softmax? People generally use sigmoids. You can use tan h also based on the data. Since the data will be always from 0 to 1, people use sigmoid only. Some 1 or 2 feedbacks also, if possible. Feedback statements. Based on that one, the next session I will plan either directly PPT or hands-on, that means whiteboard explanation also. So next session will be PPT, because the PPT that I had designed properly, it will give the proper explanation to the CNN. And I will take one example, that is MNST, regular example. Digit optical, that means digit categorization. Can I get 1 or 2 feedback statements so that I will wind up this?
Yeah, anybody from the participants, can you please give your feedback so that we can plan the next session?
Thank you so much. Thank you, sir.
Hello, thank you, sir, for this session. So actually, the part where you explain the how to adjust the weights and the examples that you have explained, along with the all the values. So it was very nice, sir, to understand how the weights are adjusted. So it was very nice for me to see the things, how the weights are assigned, how you just calculate the value of W and V, sir. Thank you, sir, for that.
Thank you so much, sir. Thank you. So, Bane, sir.
Yeah. Okay, thank you for your detailed explanation, sir. Actually, the machine learning is adjustments of the weights, and that you explained in a very nice manner. So that is actually the machine learning. So everybody, I think, understood the concept of what exactly the machine learning and how to adjust the weights.
Thank you so much. Because without this understanding, generative AI is very, it's not suggested.
Yeah. And actually, your expertise also and the ability to translate the complex ideas into digestible concepts reflects your deep knowledge and passion of teaching. Actually, you have the passion of teaching that you told that really we are all experiencing. So on the behalf of everyone here, I extend our sincere thanks to you for sharing your time, knowledge, and energy with us. So thank you very much, sir.
Thank you, sir. Thank you so much, sir.
So tomorrow we'll see again with the next session of CNN.
Day after tomorrow, I think.
No, sir, it is tomorrow.
Okay, fine, sir.
Tomorrow.
Sorry, sir.
Yeah, okay. Tomorrow 6 p.m.
Yes. Thank you so much, sir.
Okay. So we'll stop here. Thank you everybody for joining. Thank you very much. So tomorrow we'll see again at 6 p.m. Thank you. Thank you, Vishnu sir.
Thank you, sir. I'm signing off.
Yeah.
Thank you, sir. Sir, can you share the recordings of the session?
Actually, we are sharing the PPTs. Recordings we'll see. Actually, we are recording, but sharing of the recordings we'll see.
Okay, sir. Okay. Thank you.